Imagine pointing one of the most powerful radio telescopes on Earth toward what looks like an ordinary patch of sky, and suddenly detecting a burst of radio energy that began its journey 8 billion years ago. Not a steady transmission, not background noise, just a brilliant flash lasting only a fraction of a second. So powerful that for an instant it released as much energy as our sun produces over several days. By the time it reached Earth, dinosaurs had not even evolved when the signal first left its source. The question wasn't just what created it. The real mystery was how anything in the universe could produce something so unbelievably intense and disappear almost instantly. These mysterious events are known as fast radio bursts, or FRBs. Since their accidental discovery in 2007, they have become one of astronomy's greatest unsolved puzzles. Most last only milliseconds, making them incredibly difficult to detect. Miss the exact moment, and they're gone forever. But one discovery changed everything.
Astronomers detected an FRB that had traveled nearly 8 billion years before reaching Earth. At the time, it became the most distant fast radio burst ever confirmed. That meant the signal began its journey when the universe was only half its current age. Somehow, a tiny flash, lasting less than a blink of an eye, had survived billions of years of cosmic expansion without losing the information scientists needed to trace it back home. That alone was astonishing, but the real surprise came after the signal had already been detected. Using some of the world's most advanced observatories, researchers began searching for its origin. Finding the birthplace of an FRB is like trying to locate a single camera flash somewhere on Earth after seeing it from the moon. The burst is so brief that telescopes usually vanish before they can react. Yet this time, they succeeded. The signal was traced to a faint galaxy so distant that its light had taken around 8 billion years to reach us. Even more surprising, that galaxy didn't resemble the kinds of galaxies scientists had expected to produce these bursts. Until then, many astronomers believed FRBs mostly came from younger galaxies packed with newly formed massive stars. Those environments are ideal for creating magnetars, ultra-dense neutron stars with magnetic fields trillions of times stronger than Earth's. Magnetars were already considered one of the leading explanations for fast radio bursts because they are capable of releasing enormous bursts of energy in extremely short periods. But this newly identified galaxy appeared older, larger, and more evolved. Suddenly, the simple picture no longer fit. If magnetars were still responsible, then perhaps they could form through more than one cosmic pathway. Instead of only being born from exploding young stars, maybe they could also emerge when ancient stars merged, collapsed, or experienced other violent events billions of years after their birth. One discovery had just expanded the possibilities.
Then, astronomers examined another remarkable feature of the signal itself. As radio waves travel across the universe, they pass through enormous clouds of thin gas floating between galaxies. Those clouds slightly delay different radio frequencies by different amounts. To most people, that sounds like interference. To astronomers, it's a treasure map. By measuring this delay, called the dispersion measure, scientists can estimate how much matter the signal crossed during its journey. For decades, astronomers suspected that much of the universe's normal matter was missing. Not dark matter, but ordinary atoms, the same kind that make stars, planets, and people. Computer models predicted they should exist, yet telescopes couldn't find enough of them. FRBs offered an unexpected solution. The longer the signal traveled, the more information it carried about the invisible gas spread across intergalactic space. This particular burst had crossed billions of light years, effectively sampling a huge portion of the universe. It wasn't just a mysterious flash anymore, it had become a probe of the invisible cosmos. The measurements matched theoretical predictions with remarkable accuracy, strengthening the idea that the universe's missing ordinary matter wasn't truly missing at all. It was simply scattered in incredibly thin clouds between galaxies, far too faint to observe directly with conventional methods. A millisecond radio flash had helped solve one of cosmology's biggest mysteries. But that answer raised another.
If such distant FRBs could reveal invisible matter, then astronomers would need many more of them. The problem was that extremely distant bursts should be incredibly difficult to detect. Radio waves weaken over immense distances, signals fade, cosmic expansion stretches them even further. So how had this one remained bright enough to be seen? Either the original explosion was unimaginably powerful, or scientists were still underestimating the true nature of whatever produced these bursts. As researchers dug deeper into the data, they realized this wasn't simply another fast radio burst breaking a distance record. Hidden inside its journey was evidence suggesting these mysterious signals could become one of astronomy's most powerful tools, not just for studying distant galaxies, but for measuring the very structure and evolution of the universe itself. And that possibility would completely change the purpose of every future detection.
The farther scientists looked into the universe, the more valuable fast radio bursts became. Every new detection wasn't just another mysterious flash, it was another ruler stretching across billions of light years. Instead of measuring distances with stars or galaxies alone, astronomers realized they could use FRBs to map the otherwise invisible material filling the vast spaces between galaxies. Each burst carried a unique fingerprint of everything it had passed through. That transformed FRBs from a cosmic mystery into a revolutionary scientific tool. But before that vision could become reality, one enormous question remained. What actually creates these astonishing bursts? The leading candidate is the magnetar, the collapsed core of a massive star that exploded in a supernova. A magnetar is only about 20 kilometers across, yet it can contain more mass than our Sun. More astonishing still, its magnetic field is so powerful that if one were halfway to the Moon, it could erase the data from every credit card on Earth. Near its surface, physics enters an extreme regime unlike anything we can reproduce in laboratories.
Occasionally, stresses inside the magnetar crack its crust or violently rearrange its magnetic field. In a fraction of a second, an immense amount of energy is released. Scientists believe that under the right conditions, this process can generate an intense pulse of radio waves, a fast radio burst. Support for this idea grew dramatically in 2020. For the first time, astronomers detected an FRB coming from a magnetar inside our own Milky Way. It wasn't nearly as energetic as the most distant bursts, but it proved something crucial. Magnetars really can produce fast radio bursts. Yet the mystery didn't disappear. Instead, it became even more complicated. Some FRBs occur only once. They flash, then never appear again. Others repeat, sometimes days, months, or even years later. If all FRBs came from catastrophic explosions, repeating bursts shouldn't exist, but they do. That means there may not be a single explanation. Some bursts may come from magnetars. Others could arise from completely different astrophysical events. Researchers have proposed collisions between neutron stars, interactions with black holes, or other exotic processes. So far, however, none of these ideas explains every observation. The universe appears to be telling us that the story is more complicated than a single answer. Meanwhile, new radio observatories are dramatically increasing the pace of discovery. Facilities like CHIME in Canada detect hundreds of FRBs every year. Each new burst adds another point to an expanding three-dimensional map of the universe. With enough detections, astronomers hope to trace the distribution of ordinary matter across cosmic history, study how galaxies evolved, and even test fundamental models of cosmology with unprecedented precision. In other words, every millisecond flash could become a measurement of the universe itself. The record-breaking burst from nearly 8 billion light-years away demonstrated something extraordinary. If a signal can survive that unimaginable journey, then future telescopes should be able to detect bursts from even farther away, possibly from an era when the first generations of galaxies were still forming. That would allow scientists to investigate periods of cosmic history that are currently difficult to study using visible light alone. Future observatories, including the Square Kilometre Array, are expected to detect thousands and eventually perhaps millions of fast radio bursts. With such enormous data sets, researchers could build the most detailed map ever created of the otherwise invisible gas spread throughout the cosmos. Questions that once seemed impossible may finally become testable. Where is all the ordinary matter? How did the first galaxies shape the universe? How has cosmic structure changed over billions of years? Fast radio bursts may help answer all of them. But perhaps the most fascinating part of this story isn't the technology, it's the perspective. The signal that reached Earth today actually began its journey roughly 8 billion years ago. When it was emitted, our solar system had not yet formed into the world we know. Earth itself was unimaginably different. The continents, the atmosphere, every living creature that has ever existed, all of it lay in the distant future. For billions of years, that tiny pulse raced through expanding space, crossing galaxy clusters, immense voids, and clouds of nearly invisible gas, before finally encountering a planet inhabited by a civilization capable of detecting it. For less than 1,000th of a second, our instruments recorded its arrival. And from that fleeting moment, humanity learned about the hidden matter between galaxies, gained new evidence supporting one of the universe's most extreme objects, and discovered a powerful new way to explore the cosmos. That's what makes this story so remarkable. Scientists didn't simply detect a radio signal from 8 billion light-years away. They intercepted a message written not by an intelligent civilization, but by the laws of physics themselves. A message that had been traveling across the universe for half of cosmic history. And if 1 millisecond flash can reveal this much, imagine what the next one will uncover. Thanks for watching. If you enjoy exploring the biggest mysteries of the universe through real scientific discoveries, subscribe to Void Atlas and join us for the next journey into the unknown.